solutions here for questions 14 and 15 from our Hebden practice questions. All right, so we're going to look first at question 14. All right, so we've got two reactants, and we have to decide which one has a greater entropy. And that means, well, which one is in a higher entropic phase. So the rule is that gases are much more entropic than aqueous solutions, which are more entropic than liquids, which have a higher entropy than solids. And if you could imagine what these molecules do in these states, I think you can understand why that's true. Solid molecules tend to stay in one place and are quite ordered in nature. Gas molecules fly around the room at high velocity and tend to be quite chaotic in nature. And liquids and aqueous fall somewhere in the middle of that spectrum. All right, so we're going to look at question A with this rule of thumb and see what we can conclude. All right, so we know that we have liquid water and water vapor. Water is a gas. And gases are more entropic than liquids, and so we would say that H2O as a gas is more entropic, has a greater entropy, we should say. All right, moving on to question B. Again, we're comparing a gas and an aqueous solution, and even though there's twice as many chloride ions in this aqueous solution than there are gas molecules for chlorine gas, it's 2 to 1, and part of our entropy argument does have to do with if you have more molecules flying around, that has a greater entropy than fewer organized ones, but the phase plays a larger role. It's more important that you have a gas than you have two different aqueous molecules. So chlorine gas has a greater entropy. All right. How about ammonia? All right, so pretty straightforward. We just have these two phases of ammonia. We know that aqueous ammonia has a higher degree of entropy or randomness than liquid ammonia. And lastly, we have either an aqueous acetic acid or an aqueous acetate and a proton. And we can imagine that this happens in water. We put in some acetic acid, and the nature of an acid is that it produces a proton into a solution. And so the question is, will this one or this one produce a higher entropy? And they're all aqueous in nature, so that's not going to help us, the fact that it is an aqueous solution. So instead, we have to look at the numbers argument. So given that the phases are the same, aqueous, aqueous, and aqueous, the fact that these guys have two molecules flying around in different directions, and by flying I mean floating around inside an aqueous solution, rather than one where the molecules are stuck together, floating around, this is more chaotic. It has a higher degree of entropy. So the acetate and the proton, the hydrogen ion, have a greater entropy, and that is a numbers argument. Great. So now we're going to move on to question 15. So question 15 has a few parts. So we're going to look at question A to begin with, which is this reaction down here. And we've got three parts. We're going to decide which side of the reaction has a minimum enthalpy. We're going to decide which side of the reaction has a maximum entropy. So in other words, a lower energy or a more random species. All right. And then we'll deal with question 3, which is we want to know, well, is it going to go 100%, or will it not occur, or will it exist somewhere in equilibrium? And we'll talk about which situations give rise to what in a second. So let's start with part 1 for question A. We want to know about the minimum enthalpy for question A. So I'm going to say A, and I'll consider I. So the minimum enthalpy asks the question, if I look at species A and B, which are variable molecules, so they we don't know exactly what they are, and same with C and D. You can, pick an element for these to be if it helps you imagine them, but it doesn't really matter in this case. However, I should also point out that we do have this note that at least for question A, all the species are gases, and that's going to be true all the way to question D. All right, so first we want to know about enthalpy. Okay, so to answer a question about minimum enthalpy, we look on this energy diagram, and we see that the total enthalpy for A and B right up here on the axis. And a lot of that enthalpy gets turned into free energy. It gets spat into the system and turned into some sort of maybe heat or light or sound, noise, etc. And as a result, these products, these reactants, have decreased the amount of energy that they've stored inside their bonds, because that energy that the reactants had was released into the system, and the new products that are formed are lower in the enthalpy, the amount of energy that tends to be stored within the molecular bonds of the system. And if you want to get technical, it also has to do with the temperature in the system, but I'm just going to ignore that for now for ease of understanding. So I would say that the products here they tend towards, I should use the same language, tend towards minimum enthalpy. So the reaction wants to move forward to the product side, at least in terms of any enthalpy argument. Now we're going to look at our entropy argument. We're going to see if that agrees or it is in conflict with that direction. So it's the products. This is the key idea there. They tend towards the minimum enthalpy. So part 2 asks about the maximum entropy, which side of the reaction is more random in nature. And okay, so we've got one thing we would know is that all of the species are gases. So there's no phase argument to be made for the difference between A and B and these 5 C's and 6 D's. But we do know that this is more chaotic because there are more reactants. So we'd say the products tend towards maximum entropy. Oops. And so the entropy argument also wants to push this reaction toward the products. And I've been writing entirely off the screen. Okay. I do apologize for that. So I'm going to make a little diagram to explain what part of this information helps me make this decision. All right, so I would look first at my energy diagram. So I start my products with my reactants, I should say. Start at some degree of enthalpy here. And PE stands for potential energy. And then that energy is released. The energy drops as that energy is lost from the system. And as a result, our products end up having a much lower enthalpy than our reactants. So this is a lower enthalpy. And that's because they are lower down on this axis, which measures energy. This axis measures the reaction progress. So that what that means is that we're just really looking at what happens if we start at reactants and we move to products. And so that's listed in the book as just saying as the reaction proceeds. Okay, and that helps us answer this question. What about the maximum entropy? Well, we can answer the maximum entropy because we can see that we have two reactants, gas reactants. I should say gaseous. And we have, well, it looks like we go to 5 C molecules and 6 D molecules, which means we have 5 plus 6. We have 11 gaseous products. So this is more entropic, more entropy, higher entropy. I'm going to write 11 there to make sure we know those are numbers. There we go. Okay, cool. So that's how we go about this. All right, so we've decided minimum enthalpy lies with the products because they're lower on this energy diagram, and then the reactants are. We have a maximum entropy with our products because they have more species to them. They're all gases, but there are more of them over here in the product side. All right, and so the question asks, well, since the universe wants to maximize entropy and it wants to minimize enthalpy, and both of those forces are pushing toward the reactants, we would say that there's no conflict here. This reaction, we would say, goes to completion, which means we would say it goes, oops, no, not Gauss, goes 100%, which means converts all reactants to products. That's what that means. All right, cool. Now, I hope that as we go through these, maybe we can pick up the pace a little bit. So we're going to talk about B here. And for the same questions, we're going to start with 1. Which one has a lower enthalpy? So the lower enthalpy we can see very clearly on this diagram is the reactants, because they lay down here on this value of the axis, lower enthalpy, whereas the products have a much higher amount of energy stored in their bonds, and that's gained from the system. So we have an addition of energy from the system, and that's sucked in from, it could be like sunlight, or it could be like temperature. There's a lot of ways you can get energy into your system, and those are a few. Okay, and so that looks like the reactants tend toward a minimum enthalpy. All right. Then we're going to move on, and we're going to say, okay, what about the maximum entropy? Okay, well, let's take a look. Again, everything is a gas. And so which side has more reactants? Pardon me, more species, I should say. And it looks like the reactants have more to them. There are 13 species in the reactants, but there's only 2 in the products. And so just for the same reason, if I consider 4Q plus 8R, and all those different molecules all form together into 2 more highly organized molecules. Well, I have 12 gaseous reactants, and I have 2 gaseous, some people say gaseous, products. And this has more entropy. Okay, so that means my reactants also tend toward a maximum entropy, chaos, disorder. All right, so as a result, the universe wants, from an entropic argument, to push the reaction to the reactants, and from an energy argument, wants to push our reaction toward the reactants. And so we would say this reaction will not occur. Won't occur, as in the notation of the question. And that is because these two tendencies are both pushing against the progress of this reaction. So we say the reactants don't react, in other words. All right, so we're going to move on. We'll take a look at question C and question D. Let's switch it up. Let's go for some mint. All right, so question C asks the same thing, right? No. 15C. All right. So we want the minimum enthalpy, so we can look on this diagram. We can see the reactants here. They have a much higher degree of enthalpy than the products. Because the products have some enthalpy that clocks in down here, but the entropy up here is much higher, and so the products have a lower entropy. So the products tend toward a minimum enthalpy. And, maybe I'll highlight the part of the diagram that demonstrates that. So we have a minimum enthalpy here, minimum enthalpy here, and a minimum enthalpy here. Okay. And so this enthalpy is lower than the amount of enthalpy stored here. Okay. All right, and now entropy. All right, so for the entropy, I'm going to write out the reaction here. 4x, and I've got 7 y's, and they all react together to form 2 bigger, fatter molecules with all those atoms all piled inside here. And so that means we have 11, 4 plus 7 is 11 reactants versus 2 products. And which one has a higher degree of entropy? Well, it's going to be my reactants. These have a higher entropy. Okay, so we would say the reactants tend toward a maximum entropy. So that pushes toward the reactants. And our energy argument pushes our reaction toward the products. And these two different forces of the universe are in conflict. And so, as a result, this reaction lives in equilibrium. And it remains in equilibrium because these two forces are both pushing in opposite directions. And so as a result, we don't end up all the way into the product side, and we don't remain the reactant side. It's somewhere in between. And not 50-50 necessarily, but that really kind of depends on the nature of what these X's and Y's and P's and Q's really are. And all right, so let's move on to question D. Question D says, okay, we've got this G and H molecule, and when they combine, they suck up some energy from the system, and then they store that energy in all these E and F molecules. That's what that reaction says. So first I'm going to look at my minimum enthalpy. So I'll look at my two enthalpies here, and I see the lower one here. That's the minimum enthalpy. These are my reactants. These are my products. All right. And so which one has this minimum enthalpy? Well, it's going to be the lower one, so that's my reactants. They are going to tend toward a minimum enthalpy. My reactants. Okay, and for my products, I would see I have many more products than I do reactants. And so there's a higher degree of entropy with my products. So my products tend toward a maximum entropy. Oops, I was writing off the page again. All right, great. And so that forces this reaction forward into the product side. So there's two forces of the universe, an energy and an entropy argument. And if they are in conflict, just like they are previously, it means this lives in equilibrium. Okay. So we're going to move on, and we're going to look at some reactions instead. So some actual reactions. So we're going to move on to question E. All right, so we'll start again with the energy argument. So I can see that energy is a product here. This is an exothermic reaction. So I think it's easiest to start by visioning what that kind of looks like. I like to draw a little energy diagram. So I know that I've got my energy here, and as my reaction proceeds, my molecules start at one energy level, and then they convert into some other molecule, and in so doing, release energy out into the universe. So that means we're going to start with a higher degree of energy locked inside these bonds, somewhere up here. And that's my product reactants, so I'm going to call it H2SO4. I'm not going to include the phase, H2O. And then we drop, and that's negative 150 kilojoules are lost from those bonds. And as a result, we make this sulfuric acid. Cool. Wait. Sulfuric acid aqueous. Oh, I see. Great. And so what's happening here? Oh, we're just turning liquids and we're making a solution. Okay. So maybe I will include the phases, because otherwise that got me a little confused. Starting to violate conservation of mass. I had a problem with that. All right. So it looks like the reactants here have a higher energy, enthalpy, I should say, than the products. And so the products, they are going to tend toward a minimum enthalpy. Okay. And my reactants? I don't know, actually. So, okay. What about entropy argument? So, okay, which side has a more chaotic phase? And we talked earlier about this principle that gases are more entropic, have a higher degree of chaos than aqueous solutions, which are more so than liquids, which are more so than gas. And so that says that I'm going to compare these phases, and I'm going to see, oh, well, I've got an aqueous phase over on the products. So that means my products tend toward a maximum entropy. And the reason for that is because I have liquid going to aqueous. And those products have a much more entropy. All right, So what's the difference? All right, so that looks like both of these fundamental forces in the universe are pushing this reaction toward the product side. And so the universe wants to mix these guys around and form a solution rather than to keep these two liquids, I guess, from not mixing. And so that means that this system proceeds, or what are we using? We're using the phrase goes. I prefer proceeds, but the question asks for you to write goes. But it goes to completion. So that means all the liquid, H sulfuric acid, and water are converted to an aqueous solution of sulfuric acid. Great. Okay. 3 more, and then we'll call it a day. All right, so I'm going to switch up paper again. What color am I going to use? How about hot pink? How about regular pink? Because I can't find my hot pinks. All right, so on to question G. All right, so F, pardon me. All right, so we'll start with I, which asks about enthalpy. And so I think it's good to draw an energy diagram. That helps me think about it at least. You can choose whether to do this or not. All right, so it looks like the change in enthalpy is 311 kilojoules. So what does that mean? How do you get a positive change in enthalpy? Well, you will remember that a change in enthalpy means your final enthalpy minus your initial enthalpy. And that's just a general principle of measuring change. It's your final minus your initial. However, in chemistry, we usually think about our products as our final form, and we're going to take away the enthalpy of our reactants. Okay, so if our enthalpy change is positive, that means the products must have had more enthalpy than our reactants. So I can emphasize that idea by drawing my H product big and my H reactant small. And that's how I get a positive value for my change in enthalpy. Is if my products have a higher enthalpy than my reactants. All right, so now I can draw my energy diagram. I know my reactants are going to start lower, and they're going to increase until I form my products. And so I'm actually going to draw that out. So I've got some C2H6. What's that? That is ethane gas. And that's going to mix and form some ethene gas, or ethylene gas, some people call it. And that is the gas that's produced by your bananas when they are ripening, and some hydrogen gas. Okay, and I know that these molecules are sucking in a bit of energy from the system in this reaction. So another 311 kilojoules of energy are all getting stored in the bonds of these molecules. Okay, and so we have a lower enthalpy in the reactants. And they tend toward a minimum enthalpy. Okay. How about an entropy argument? All right, so what do we got here? We have all gas species, but the reactants have 3 different, the products have 3 different species in them. The reactants only have 1. So 1 gas reactant turns into 3 gas products. So as a result, it's a numbers game. We make a more chaotic system if you have 3 bodies flying around than if you just have 1 organized one. And so as a result, this has a higher entropy over here. And so we would say that the products tend toward a maximum entropy. All right, and so question 3. Well, since our enthalpy argument pushes the reaction to the left. The entropy argument pushes a reaction to the right. The result is that we are going to have a system that lives in equilibrium. Two different forces opposing. All right. Moving on to G. All right, so we have ethine. Oh, interesting. Okay, I don't see that much. All right, so gas is going to be mixing with some calcium hydroxide in an aqueous solution. And it's going to make some calcium carbide and some water. Calcium carbide, huh? All right, well, again, we're going to look at our enthalpy argument here. And okay. So I'm going to start with this enthalpy. This says that we've got a positive change in enthalpy. Okay, so again, that means that I must be subtracting a smaller set of enthalpy from my reactants than my products. Because if I take away a small number from a big number, I get something positive. If I take a big number from a small number, I get a negative value. All right. So that tells me that my reactants have to be at a smaller enthalpy. But I think it's still good to draw a little diagram, so I'm going to draw a little sketch there. This is my reaction. This is my potential energy stored within the bonds of the system. And all right, so I'm going to start with some lower enthalpy reactants. They're going to gain 183 kilojoules of enthalpy for every mole. And I'm not going to write all these reactants out. I'm just going to say reactants and products. And so we have a lower enthalpy here, lower reactants. And that's how we get a positive change in enthalpy. All right, so that means the reactants tend toward a minimum enthalpy. All right, and that pushes the reaction to the left. All right, and then we've got an entropy argument. Okay, so what do we have here? We've got some gases on the left, an aqueous solution on the left, and a solid and a liquid on the right. So both of these phases are more chaotic in nature than these two states. And so that means that our we have gases plus an aqueous solution, and they move to a solid and a liquid. So these have a higher entropy. That's the argument. Therefore, they have a higher entropy. So our reactants tend toward a maximum entropy. So again, we're pushing to the left. And so that means that our system does not occur. It won't occur. This reaction does not proceed. And it doesn't proceed because there's two different fundamental governing forces of reactions that both keep the reaction at bay. Okay. Last question. So we're going to talk about question H. Question H. Piece of paper. It's going to be yellow. So for question 15H, so I've got some carbon mixing with some oxygen gas, and together they're going to make some carbon monoxide. All right. And it looks like this is going to suck in some energy from the... No, pardon me. This is going to release some energy into the system when this reacts. All right. So I'm going to start here. I'm going to start with this negative 20. So delta H is negative 221 kilojoules. Okay, so that tells me that I have a negative delta H. And how do I get that? Well, delta H is my H of my products, take away my enthalpy of my reactants, I must have to have been taking away a larger enthalpy from a smaller one in order to get a negative value. That's how you get negative numbers with the subtraction. So that means my reactants must have been higher up on an energy diagram. So if I draw that, reaction, so that means my reactants are going to be way up here. So my 2 carbons, which are solid, and my oxygen, which is a gas, are going to live up here. They're going to have a higher enthalpy. And then we're going to drop down here, and in that process, you're going to lose 221 kilojoules from the system. That's going to be released as heat or fire, plasma, or like a noise. Who knows how that energy is going to be released? Question mark, question mark, question mark. Who knows? We know that it's lost from our system, and as a result, we get 2 carbon monoxide molecules. All right. And so we see the products here have a smaller enthalpy. So the products tend toward a minimum enthalpy. Okay. And then I look at my entropy argument, and I can see that I have 2 solids and 1 gas forming 2 different gases. And so 2 gases are more entropic, more chaotic than a single gas, even if you have 2 solids. More gases just make the system much more chaotic in nature. And so this is more entropy. All right, and so we're going to say the products tend toward a maximum entropy. So as a result, our reaction proceeds 100%. All reactants are turned into products. Okay, so I hope that helps, guys. I know that thinking about entropy and enthalpy, and having these terms that are so similar in nature, can be confusing. So practice, let me know if you have any questions, and seek help when you need it. All right, good luck studying.